All right, let's go ahead and get started. Any questions about anything before we get back to it? Okay, so talking about these Taylor series, Maclaurin series. Essentially, now we can take any function, as long as that function, you can take derivatives of it, like over and over and over again. We can build series for those. We can build Taylor series. So, the last one we did was this sine of x. So let's go to another example. Yeah. Amazing. So I want to find a Maclaurin series for this thing. So f of x equals x cosine x. How do we do that? How should we get started?
Coefficients.
Okay, how do we get those coefficients? So
Function at 0.
how do you know it's at 0?
Because it's a Maclaurin series.
So by definition, Maclaurin series is centered around the point x equals 0. So f of 0 is 0 cosine 0, which is 0. What is C1? F prime of 0. Okay, so I need a derivative, right? How do I find the derivative of x cosine x? So I need the product rule. I mean, this is, I kind of have to treat this as the product of two distinct functions, x and cosine of x. So what's the derivative of x cosine x? Okay, so let's call these things g and h, since we're already calling the whole thing f. So how does the product rule work in general?
H of x times g prime of x.
G prime h plus g h prime. So for us, what does that look like? 1 times cosine x plus, or I guess minus x sine of x. That look right? Okay. If I plug in 0 to all those x's, what should I get? Looks like it's going to be 1. Question so far. All right, how would I get the next one? How would I get C2?
Zero divided by 2 factorial.
Yep.
2.
Yep. All right, so what's the second derivative of our function? Do we need the product rule again? We should. So cosine of x we don't. So what's the derivative of cosine? Negative sine of x, and then now we got to handle x sine of x using the product rule. So minus, let's just follow the template that we put out here. The derivative of the first term is 1. So times sine of x minus the first term, which is x, times the derivative of sine of x, which is cosine x. So I got negative sine of x minus sine of x minus x cosine x. I can combine a little bit. I get negative 2 sine x minus x cosine x. So if I plug in 0, what do I get? Negative 1. I think it should just be 0.
Oh, okay.
Yeah, x. So yeah, cosine of x is 1, but I'm gonna 0 that out. So 0, 1, 0. Do we have any kind of idea what pattern is showing up yet? Anything at all?
Like
That seems like a what?
It's either the cosine of X or the sine of X pattern that we already went through. 0, 1, 0.
So, and let's go back to the sine of X, since you're seeing some similarity. So with that one, we saw that every even term was absent, right? Every even coefficient was 0. With this one, are we getting the same thing? Or is it offset? Seems the same so far, right? So let me ask you, before we go any further, what's making this like hard to do? Like we kind of ripped through this sine example. I think the most of what we talked about with the sine of X was how to deal with the fact that so many of these terms or so many of these coefficients are 0. But with the derivatives, we handled those very quickly. So why was that part of that example easy to do and this is not? What's the issue here? Derivatives, and what in particular makes the derivatives hard to deal with? Product rule, right? What if we didn't have to do it? So let's start over. Keep in mind why let's go back to basics. Why are we doing a Taylor series? Basically, what a Taylor series allows us to do is, if I can take a function that looks like, anything, no matter what it looks like, as long as I can take derivatives of it, as long as I can take an infinite number of derivatives of that function, then I can make, by doing a Taylor series, I can make it look like this: C0 plus C1x plus C2x squared plus C3x cubed, and so on. But we said that our function was kind of already written as the product of two things, right? This x and this cosine x. Let's talk about those parts individually. Doesn't x already kind of look like this? I mean, it's obviously this has a lot more stuff going on, but I think if I wanted to represent x that way, I could just say, all right, C1 is equal to 1, and all the other c's are equal to 0. Does that make sense? So really, it's the cosine that doesn't look like this, right? If we could find a way to just turn cosine of x into a power series, I think we could just multiply them together. Does that make sense? Basically, what I'm saying is this. I know that so let's just say in general, f of x is equal to g of x, h of x. If I can find a power series for g and a power series for h, shouldn't I just be able to multiply those together to get the power series for f? Okay, that's what we're going to do. So in our case, g of x is x, and h of x is going to be cosine of x. G of x already looks the way we want it to. It already looks like a polynomial. So because of that, let's just turn h of x into a power series. So we need some derivatives, right? What's the first derivative of, not f, h? What's the first derivative of cosine x? Negative sine x. What's the second derivative? Negative cosine x. The third? Positive sine of x. And then the fourth? So just like sine, it has like this 4 cycle to it. If I ask you for the 91st derivative, you could figure it out without calculating 90 derivatives. So let's rely on that. And we've freed ourselves of using the chain rule. So let's find the first few terms now. So how do we find C0? Yeah, so C of 0 is equal to cosine of 0, which is what? 1. C of 1 is equal to negative sine of 0, which is 0. C of 2 equals negative cosine of 0. Not quite. Over 2, right? Which is negative a half. What should C3 be? 0. So positive sine. So every odd derivative of this is going to be a sine term, right? What's the sine of 0? Always 0. All right, C4 is going to be positive cosine of 0 over 4 factorial, which is 1/24. Okay, so what does this allow me to do? I've got those first 5 coefficients, so I can write down some terms. So cosine of x is equal to 1 minus 1/2 times what? X squared. Why is it x squared and not x? So, and that's one thing, I got a lot of questions from like the last web work about this, is that basically the way that, I think the most consistent way we can talk about these power series is that the subscript on whatever these C coefficients, those need to go in lockstep with the powers on x. So if we follow that definition, C2 is the coefficient of x squared. And then what's my last term, or my last non-zero term I know about? 1/24 x to the 4th. And then I could find more, but I'm going to try to stop here. Do we see any kind of patterns emerging? So we see that, like, which terms am I going to be missing? All the odd terms you could be missing, right? And then what can I say? Can I say anything about the even terms, the ones that are actually going to be non-zero? They're going to be fractions. Can I say anything about the numerators and denominators of those fractions? Numerator will be 1, so the numerator is going to be 1. What would the denominator be? So it went from 1 to 2 to 24. It's the factorial of whatever the power is, right? So let's try to put it all together. What's happening to the powers of x? They're increasing by 2 each time, right? So I'm going to write this down, and you can tell me if this is okay. Is x to the 2n make sense? So we had a little bit of the issue with the sign because we were off by 1. We had to account for that, but will x to the 2n, will that give me what I want? In this case, I think it does. Over what? Yeah, so you said the powers on x are going to mimic whatever the factorial of the denominator is. So, sorry, like, Nimrata said that. Credit word student. No, it's not okay. I know who you are. So just like the sign, I mean, even though the exponent and that denominator, just like in the sign, they were the same as each other, but now they're off by a little bit, right? Does this h of x that we define, are we satisfied with that? Okay. So let's incorporate, I like to put that first. -1 to the n, does that work? Does that alternate in the way that we want? I believe that it does. So the first power is going to be 0, or the first value of n will be 0. -1 to the 0 to the +1. I think this works. So this right here, we're not done, but we've turned cosine of x into a power series. So based on that. How do I put it all together? What's my power series gonna be for x cosine x? H of x times x, so what will that do to this definition of the power series?
X,
X to the 3n, I don't
or
know,
X to the 2n plus
x to the 2n plus 1 over 2n factorial. How are we doing? Let's try to do something with x. I'm gonna do it in the margin because you'll see why this works. So I called this g of x, right? G of x equals x. I want to make a power series for x. How do I find the first term or the first coefficient in a power series?
zero.
So g of 0, which is what? 0. How do I find the next one? G prime of 0. So what's the derivative of x? If I plug in 0, there's nothing to plug 0 into. It's just 1, right? And that's exactly it. So basically, C2 equals G double prime of 0, which is 0. And what will all the higher derivatives of this thing be? 0. So if I build up this Taylor series for x, I'm going to get C naught plus C1 times x plus C2 times x squared. So we said C naught was 0, right? We said C2 was 0. C1 is 1, right? So our power series of a polynomial ends up, so this will be true. This is true for x. Basically, our power series ended up just giving back x. That will happen anytime you have a polynomial. Because basically, think about when we first started talking about this on Wednesday, the way we built up these Taylor series is by taking a bunch of derivatives and making sure those derivatives agree with the original function. And you're going to do that to construct a polynomial. So a thing that looks like this. A bunch of terms added together with ascending powers of x. If that's the place we start from, and we're trying to build something that looks like a polynomial, we're just going to get the same thing back. So that's exactly why I can just take the x and reincorporate it. Something else I want to point out. The power series we built for cosine is the thing we call H, right? We previously did one for sine, right? Power sine and cosine, among other things, there's a relationship between sine and cosine through calculus, right? What is that? Like, one is the derivative of the other, right? Cosine is the derivative of sine. So if we look at sine, so we built this last time, right? This is the derivative of sine, right? If we take a derivative of this, what do we get? You should, I mean, you better, they'd better be equal, but let's take a derivative to make sure.
X.
So if we do a derivative of this, we get this series. -1 to the n is a constant as far as x is concerned. What happens to x to the 2n plus 1?
Or 2n plus 1 x.
Oh, I didn't leave myself enough room, so I'll do this. X to the 2n plus 1 over 2n plus 1 factorial divided by 2n plus 1. Can I simplify it all? The 2n plus 1 factorial over 2n plus 1?
2n plus 1, or the x to the 2n plus 1 should be x to the 2n, should be.
Yeah, thank you, it should be. So that's correct.
And 2n plus 1 factorial could be 2n plus 1 times 2n factorial.
Right. So we usually go the opposite direction, but in here, I can pull out that 2n+1 term out of the 2n+1 factorial. And cancel it out with 2n+1 below it, so I'll have 2n factorial. So. These Maclaurin series, Taylor series, once you've made them, they are exactly equivalent to the things that you made them from. So the derivative of one better be the same thing as the derivative of the other. How are we doing so far? So what about radius convergence? Where does this thing converge? Do we have to do a ratio test to see where it converges?
Equal. Sine of x was 1. Or wait, no, it was all real numbers, so
Okay.
it should be all real numbers.
Why would they be the same? So let's go back and looking at sine. We found out that the Maclaurin series for sine converge everywhere. But Caleb, you're saying because of that, x cosine x converges everywhere. Why is that true?
Well, cosine of x is the derivative of sine of x.
That's enough. So that's one thing we talked about a couple class periods ago, is that if a power series has some radius of convergence, its derivative will have the same radius. But one thing we should also talk about is, well, it's not really the derivative because we incorporated this x thing, right? The radius of convergence of a polynomial is always absolute. It's always all real numbers. How are we doing? Go ahead.
When you go from h of x to f of x, the x with 2n becomes 2n+1.
Yep.
+1.
Good question. So let's look at the way we define these things. What is the difference between h and f in the way we define them? Like how do I, in other words, how do I get from h to f? So let's reset all the things that I said here. I said that f of x is equal to the whole function. And then we broke that down into two smaller functions. G of x equals x and h of x equals cosine x. So essentially, if I want to turn h of x into f of x, I have to multiply h by a single power of x. So what I didn't show in here is this. Maybe I'll rewrite it like this for now. Because of that, I can rewrite this as basically this whole thing right here that I'm kind of hovering over is h, and I want to multiply that by x, which is x to the third power. So combining that x to the 2n and x to the 1 gives us x to the 2n. That's what I think. Good question. What else? Okay, so if you can separate out polynomials from these things, that way you're making power series out of, less moving parts. Probably be a lot easier for you. So one thing that shows up a lot is this idea called a binomial series. So in general, what does that mean? A binomial series is anything that looks like this form. So basically, called a binomial series, which so two terms added together raised to any power at all. So basically, we're going to build a formula for how to deal with these things because they show up quite a bit. So we want to build a Maclaurin series for this thing. So let's do it. How do we build a Maclaurin series? Coefficients. So let's get the first one. What is C naught? Probably simplify it more than that.
Oh, just 1.
Yeah, this becomes 1 to the power of k. Just 1. What's the next one? So the derivative, so this becomes k times 1 plus x to what power? K minus 1. So it's k, right? Next one. Second derivative over 2 factorial. What's that derivative? So yeah, how's that gonna come out? So that comes out to be, so let's not forget the thing that I forgot. K times k minus 1 over 2 factorial. What do we think the next one's gonna be? Do we have any sense of what's happening yet? That is absolutely what's gonna happen. Bella, do you have a question?
Yeah. So, do we always do it over the 2 factorial?
Yeah, in fact, and to be totally clear, I don't put them in because they don't mathematically alter anything, but we can do that whole trend, that whole thing from the beginning. So this should be f of 0 over 0 factorial. This should be f prime of 0 over 1 factorial. Yeah. Yeah, so. Yeah, the reason we leave them off the first two is they're not altering. How we doing? Should we do one more, or are we kind of seeing what's happening? Now let's do it. What's the next one gonna be? So basically, this is the pattern that kind of comes out of these. So it's a shortcut I wouldn't heavily encourage you all to use, but I didn't want to give it to you away for nothing. I wanted you to kind of see where it came from. But basically, that's what these series look like. If I have something that looks like this, 1 plus x to the power of k, it equals 1 plus k plus k times k minus 1 over 2 factorial. You know, basically it just continues on like this indefinitely. So questions on how we built that before we essentially use this as a shortcut to do other things. Okay, so let's try one. So I'll put a kind of a reminder. Here's what we're shooting for. Can I make my function look like this? 1 plus x to the power of k. So we have a little bit of work to do to get there, but so let's start doing the work. How can we start making the f I gave you to fit that, basically to fit the forms, we can start using that binomial series shortcut.
Bring the root to the numerator,
Okay,
so it's just like 4 minus x to the -1,
-1, you're on the right track.
or I mean -1.
-1/2, good. Excellent, are we done? Let's see some head shakes. Why aren't we ready? That 4 is a problem. So how can we deal with that 4? Divide by 4. Can't really divide because then I'll fundamentally change it, but I can. That's the same thing. But there's a thing that's like division we can do that is not going to change. It won't really change anything. Yeah, I can factor it out. So if I factor it out, I'll be okay, because you're kind of doing, basically you're doing part of what division is, but you're also not removing the factor entirely. So if I factor that out, I'll have 1 minus what? 1 minus 1/4 x to the negative 1/2. And I factored out my 4, right? Did I really factor out a 4 though? Basically, we factored that 4 out, but then we write this in a different way. I kind of have to factor inside the bracket. So I factor out a 4 and I get this 4 times 1 minus 1/4 x, and then that whole thing is raised to negative 1/2. From there, I can say this is equal to the same, this is the same thing as 4 to the negative 1/2 times 1 minus 1/4 x to the negative 1/2. What is 4 to the negative 1/2? 1/2. Sounds good. Why is it 1/2? It's 1 over the square root of 4. So 1/2 times this thing, 1 minus 1/4 x to the negative 1/2. Now are we ready? So now we're good. We have the first term 1. We have this binomial, we have the power. So basically, we're going to carry this 1/2 and set up, let's say 4 terms. It's really, there is no end to this. What's the first term going to be? Well, I'm going to keep the 1/2 away from this. Basically, we're gonna expand the thing inside the parentheses. So we're gonna just expand the 1 minus 1/4 x to negative 1/2. So if we want to go back and remind ourselves of basically what's the shortcut we bought ourselves, looks like this. So maybe it's a good idea for us to write down what our k is. What's our k for this one? Negative 1/2. I think that should be enough. So what's our first term going to be? First term is always just 1. So that's kind of comes from us writing this out the way we did. Second term should be what? So minus 1/2. What's the next term? Oh, I left off something really important in here. Oh, so bad. These are all just constants, right? I didn't take the powers of x that really need to go with them. What's that? Not quite. One more thing we have to be wary of is that coefficient is negative 1/2, right? But we don't really have just x, right? What is our variable term inside that binomial? It's really negative 1/4 x. Does that make sense? Okay, so let's back up. Maybe we should generalize this a little more. Instead of saying this is 1 plus x to the k, let's replace this with an a. If we replace that, then let's see what changes with our derivatives. So instead of saying this is 1 plus a, or 1 plus x, we'll say it's 1 plus a. Does that change it? So C0 is still gonna be 1. Is C1 still gonna be K? Or is it gonna change a little bit? Let's remind ourselves, in general, how do we find C1? So C1 comes from the derivative, right? Let's actually take this derivative. What is the derivative, the first derivative of 1 plus a to the k? K times 1 plus a and k minus 1. Is that enough? Why not?
As you need to do the cheat.
Right, so we need the chain rule. So what's left? Whatever the derivative of a is with respect to x. Why didn't we do any? Why didn't we look at chain rule for any of the stuff that came before the first time? It was so the inner function was 1 plus x, whose derivative is 1. But in general, we might have to worry about that. So I'm going to modify the C1. So if I plug in 0 for x, by the way, one thing we're kind of banking on this, a of x will be equal to, like, I'll say nx, some multiple of x. So because of that, there's not going to be any like constant term. So plugging in 0 for x makes the whole thing a, it makes all of a equal to 0. Okay, so how does that, let's look back at our general C1. So we originally just called this K, but how should we modify that based on what we just talked about? K times dA dx, right? How about for C2? So let's see, let's actually take the derivative over here. What is the second derivative of this?
-1
K times K minus 1.
times CATX.
Oh, we missed something.
Okay, I'll do 1 plus a.
Oh, I see what you're doing. Okay.
K plus 2 times DATX times DATX.
Right, so basically another power of this dA dx, right? So if I start making the modifications to what I have down here, instead of 1 plus k to the x, it should be 1 plus k times a times dA dx. And then how about that next term? If I plug in 0 for a, I should get k times k minus 1 times 1 times dA dx squared times a.
A squared.
A squared, yep, all over 2 factorial. So yeah, looking at it in terms of x is more simple, but probably hides a lot of the things you need to pay attention to. So in general, that second term is not always going to be as simple as x. So now that we've reset things, how are we doing? So these A's come from how we, in general, how we find a Taylor series. Um. Let's get rid of this, we didn't actually find them. But in general, a Taylor series or a Maclaurin series looks like this. Or I guess a power series in general looks like this. C sub n x to the n. And that all comes from basically we want the function we want to turn into a power series. We want it to agree completely with the power series itself. So we want the one point that one point where they're centered to be in common and all the derivatives. Like all orders of derivatives to be equivalent to each other. The only way to do that is to have the powers of x follow suit with each coefficient. What else?
To clarify, it would be. Like the case for it to be 1 plus k times for the a that we were having, 1/4 -1/4 x times -1/4. It's not just x times -1/4.
Yeah, it should be 1/2 times.
Well, yeah, that's the k 1/2 times. I'm just confused if it's x times dA dx or if it is a times dA dx.
So
based on how we
let's
define
look at it
A.
again. So maybe I should start with let's pick a new slide. Right, so how about this? Instead of saying that a is a variable to itself, let's say this f of x is equal to 1 plus ax to the k. So a is a constant. Okay, so yeah, let's kind of restart. So instead of just saying that instead of saying that second term will always be x, let's say it'll be some multiple of x, which it could be. Are we okay with this redefinition? So let's just start building up again. How do we get the first coefficient? That's f of 0, right? What is f of 0? Still 1. What is C1? F prime of 0. So what's that going to be? K times 1 plus a x to the k minus 1 times a. So if I plug in 0 to that, what do I get? Okay. Next one. F double prime of 0 over 2. What's the second derivative? Times 1 plus a x k minus 2 times a squared. If I plug in 0 for that, what do I get? Do we think we can say what C3 is? Okay, so it looks a little bit similar to before, but not quite. So that's just generalized now. So f of x will be equal to 1 plus Ka x, right? Because the coefficients are going to be free of x, but then when I bring in the powers of x, I'm going to have Kax plus k times k minus 1 over 2 factorial. And what's squared? What do you prefer, ax parentheses squared or a squared x squared? All right, sounds good. One more for good measure. K times k minus 1 times k minus 2 over 3 factorial times ax cubed and on and on. All right, so you'll have taught me that I just need to start with the most general form of this before I try to build up to it in the future. How are we doing? Does it make sense? So I think this is in substance identical to what we did before, but I very much muddied things. Hopefully we're good now, or we're better. Cool. All right, so now let's apply that to this. So k is still a half. What's my a? -1/4. So I think now that we have those two moving pieces to worry about, I think we're okay. Having said all that, we set up those first two terms. Are we still happy with them? I believe you said that, so we just said the second term should be Kax, right? I think we have that. In fact, I'll not rewrite it. All right. What's the next term gonna be? So plus -1/2.
-1/2 minus 1.
So -1/2 minus 1.
Minus x squared.
What did I say, 4 terms before? 3 is good.
I think you're missing a parentheses.
Probably, but where? The 1 and 1.
Yeah.
No, I think this 1/2 should be here.
Yeah, I know, but you have like that parentheses.
Oh, on the far right?
Yeah, you don't have a close parentheses.
Okay, yeah, no, I agree with that. So, building up the first 3 terms, how are we feeling about what we've done? Okay,
So this is something that was kind of forgot this way, or is it something we should like try to identify?
I'm not sure what you mean.
So we said like the form, the rule next to the K.
Yeah.
Is there something that like kind of appears for some of them, or?
Yeah, I mean,
Find
it won't, like, I don't think it's obvious in this one. Other than the fact that we just talked about the generalities and I showed
I'm
this.
just trying to figure out what we can put
I don't know if giving it away is, I mean, the thing I would look for is a binomial. So if you have 2 terms added together
there.
under, bracket, under a power, yeah. Which I think this is not totally obvious if that's the case. But I would be on the lookout for that. Here's the thing, even if you don't notice it, you can still write, you can still do all the general Maclaurin series, Taylor series stuff. That's really all this is. This is a special case of that. So we got like a minute left, so yeah, let's go ahead and simplify. What's the second term going to come out to be? 1/8 x. And the next one? Positive or negative, first of all? I think positive. So 1/2 times 3/2 is 3/4. Times 1/16, which is, yeah, the 1/4 squared itself becomes positive. So 3/4 times 1/16 is 3/64. Divided by 2 is 128. Someone double check me. I feel like I took a lot of those factors fast. So all told, 1/2 plus 1/16 x plus 3/256 x squared. Okay, I'm over 11, so yeah, we'll pick this up next time. Got like 1 or 2 more things from this chapter, then we'll move on to the last chapter in Smith. Right, see y'all next week, or I'll see you in office hours.